Welcome back. As promised, we are going to study the error analysis in Euler's method. So let me start sharing the slides and we will review Euler's method once. We will just see what the method tells us. Okay. I hope you all are able to see the slides by now. So what we are going to do is that we start with an initial value problem. So we have this differential equation here, dy by dt is equal to f of t comma y. And this equality is valid over the interval a to b. And we also have the initial value, which is that the function y, which is a solution to this equation, its value on a is equal to alpha. This is the initial value problem. And what we then do is to give approximate solution to equally spaced nodes in AB. We are not giving a function. What we are doing is that at various points inside this interval AB, we give the approximate value that the function would then have. Okay. So this is what we are doing, and the methods the method begins by choosing a positive integer capital N, letting small h to be the division of b minus a by n. This will be the step size between those nodes which are the equally spaced nodes. So a single step size will do. And then we take these nodes ti, which are a plus ih. So they will be a plus h, a plus 2h, a plus 3h, and so on all the way up to b. That's what we have. So we have these ti. Then we start with w naught, which is the approximate value at t naught, and t naught is a. The function is supposed to take the value alpha, so we take the value of w naught also as alpha, and then we use Taylor's theorem. So Taylor's theorem would say that the value at t1 is approximated by the value of at t naught plus h times the derivative value at t1 or at t naught. So that's what we are going to do. So we have wi plus 1 would be wi plus h times f of ti wi. So this is the Taylor's theorem, which helps you giving the approximate value. Taylor's theorem gives you an error, and that error is being ignored here. Therefore, this is an approximate value. So this is Euler's way to give the approximate values, and we have done an example in the last lecture with two different values of n, and now we are going to study the error pattern. Okay, so let's state it as a theorem. Suppose we have a continuous function f, and suppose this continuous function satisfies the Lipschitz condition with the constant capital L on a vertical strip, infinite vertical strip. Okay. Assume that the unique solution yt, the existence of this unique solution yt was seen in the previous lecture. It's a result that whenever you have a continuous function which satisfies a Lipschitz condition, then the corresponding initial value problem has a unique solution. So suppose this unique solution satisfies y double prime being bounded above the absolute value of y double prime being bounded above by capital M. Okay, this is what we assume. Then for these Euler approximations wi, the difference of yi and wi is less than or equal to h, which is the step size, capital M divided by 2 times L. L is this Lipschitz constant here. And inside bracket, we have some exponential value -1. So this exponential value in the bracket depends on the I that we are looking at. So it is going to be e power capital L ti minus a -1. So as you go far away from a, this error in the bracket is going to increase. The constant outside will remain unchanged. It will remain constant. It doesn't change as I changes, but the quantity in the bracket will change as I changes. And of course, if you put the value I equal to 0, then we immediately notice that the bracket small this round bracket here, ti minus a, that will give you the value 0. So L into 0 is also 0. You have e power 0. E power 0 is 1, and therefore this whole quantity in the square bracket is going to give you the value 0. And indeed you have y of t naught minus w naught is in fact 0. So if you make an attempt to give a proof of this, I'm aware that we have not given many proofs, but let's try to give some brief idea of the proof here. So the result is clearly true when I is 0. We have seen that just now. And now try to derive the result using induction. So y of ti is going to be denoted by yi, and yi plus 1 minus wi plus 1. Okay, so yi plus 1 is equal to yi plus h f of ti yi plus h square by 2 y double prime xi. So the terms here, the first term here yi, the first term here h into f of ti yi plus this h square term. This is all part of the yi plus 1. And we are subtracting wi plus 1. So we get wi with a negative sign, and we get f of ti yi multiplied by h with a negative sign. So this is the equality. yi plus 1 minus wi plus 1 is yi minus wi plus h times f of ti yi minus f of ti wi plus h square by 2 y double prime xi for some xi between yi and yi plus 1. This is what we will have. Now we want to put a modulus sign on both sides, and the right hand side is a sum of certain quantities. So we can bring the modulus sign inside and get a less than or equal to sign. Moreover, we observe that here this quantity inside the square bracket is something which has the first coordinate to be the same. So it is f of ti yi minus f of ti wi, and our function is continuous, but moreover it satisfies the Lifshitz condition. So that would mean that this highlighted quantity in the modulus sign is less than or equal to L times yi minus wi in the mod. And we have the first round bracket involving yi minus wi anyway. So this mod of yi minus wi will be taken common, and we have 1 plus hl. Once again, this contributes 1. The round bracket, when we put modulus, will contribute 1, and this square bracket will contribute L. And then after all, y double prime xi is assumed to be bounded above by the constant capital M. So that will give you h square m by 2. So for the ith error, we have a formula in terms of the I minus error. And now we use the induction to get the formula in terms of the I minus. So okay, so I plus 1th error is in terms of ith error, and now we write the ith error again in terms of I minus 1th error. So similar to this formula on the right hand side, we will use a similar formula for this yi minus wi. So that will give you yi minus 1 minus wi minus 1 multiplied by 1 plus hl, and you add h square m by 2 to that. So this is the quantity we get. So if you keep doing this all the way up to 0, you will have several powers of 1 plus hl which will come. There will be some constants which will come. So ultimately, what we get is e power I plus 1 hl, and then you have mod of y naught minus w naught plus h square m upon 2 hl minus h square m upon 2 hl. So this proof is slightly involved, and so we are not going to go into too much details of this. We will anyway not be expecting to have this as a question in the examination, but this proof can be found in several books. The books that I have mentioned to you as reference books will have proofs of these steps. So once we have this, then all we need to do is to write, because y naught minus w naught is 0. We know that at 0th step, of course, y naught is equal to w naught. So it is just h square m upon 2 hl, and outside also you have the same quantity. So it is e power I plus 1 hl but e power I plus 1 h is simply t I plus 1 minus a. So we get the final formula that the I plus 1 actual value and the approximate value, the difference between them is less than or equal to capital H into small h into capital M, the step size, into the upper bound for the second derivative, divided by 2 times the Lifshitz constant, and in all this is being multiplied by an exponential value minus 1. So this is the actual formula that we have, and of course we see that when h is small, of course we would expect that the error is very small. Or whenever you are looking at capital N being larger, we saw in the example that if we take more nodes, that would mean that the step size h is smaller, then the accuracy is slightly better, which is also seen here in the error formula. Okay, so now whenever we talk about errors, there are two types of errors. But first of all, the problem here is that we need to know a bound for y double prime of t, because this capital M that has appeared here, this is the upper bound for the modulus of y double prime t. So that is something that we need to know. We may not know about this because we don't know to begin with what is the solution yt, and although y prime t is f of yt, but y double prime with respect to t would be the derivative of the function f with respect to t, and that involves derivative of y also with respect to t. So that is something which we don't quite know, but in sometimes if you have information about the partial derivatives of the function f with respect to t and with respect to y, then the chain rule here will tell you how to compute the second derivative. So even if you don't have any information about how to write the function y and how to compute the derivative of the function f with respect to t, because that will involve a term where you have to compute the derivative of y also with respect to t. Without that, if you know the partial derivatives of the function f with respect to t and y, then you can write this quantity, and that will therefore allow you to obtain an error bound for y double prime t, although we will not know the function yt at all. So the principal importance, as I told you, that the bound depends linearly on the step size. If you make if you divide h by 2, the bound on the error will be divided by 2. So it depends on the linear factor of h. It doesn't have any higher powers or no other power of h are involved. So of course, whenever you reduce the step size, it will give you greater accuracy for the approximations. Okay, now the second type of error is the round off error. So this error that we saw was the truncation error, which appears because of the approximation, assuming that all the numbers are taken truly as the real numbers. But there will be round off error because we will not take real numbers as real numbers. We will convert them into finite decimal expansions, and therefore there are bound to be some round off errors. In fact, if you are taking h to be smaller, then there are more calculations involved, and then the round off error will become even worse. Okay, so more round off error will be expected if your h is smaller. So what we are actually going to do is to not have w naught equal to alpha and wi plus 1 to be wi plus h f ti wi. What we will be doing in practice is that this alpha is being added by some delta naught, and the ui plus 1 instead of wi plus 1, we will have ui plus 1, where the error, round of error, delta I plus 1 will be added at each step. That is because of our calculation limitations. Okay, so this delta naught, delta 1 up to so on, these are the round off errors, and we did not consider the round off errors earlier. Now we will try to get a bound using the for Euler method, assuming that there is a round off error. So this is how the error is described. This is our initial value problem, which we have to mandatorily state whenever we are talking about a result. Suppose u0, etc. These are the approximations with round off errors delta I. And typically what would happen is that the round off errors would occur because we limit ourselves to take, say, 5-digit approximations. The number representation that we choose, we will fix some number of digits. And therefore, we will have an idea about the maximum value of the round off error. So we assume that this delta that is here, this is the maximum value. It's a bound, upper bound on the round off errors. Okay, that delta is important. Then the actual error, so YTI minus UI. In the previous formula, we had WI because those were our approximations. Here UI are approximations plus the round off error. So this difference is less than or equal to, now the formula is slightly complicated. It is 1 upon n L HM by 2 plus delta by H. Inside the square bracket, we have the usual exponential some quantity minus 1, and we have added error which is mod of delta naught e power L Ti minus e. So if your delta naught is 0, if your alpha happens to be an integer, or if it's a rational number which has finite decimal expansion, then you will have possibility that this delta might be 0. And in that case, this second part of the error will not occur. But the delta may still be there because it's the bound of all, the upper bound for all the round off errors. So this is what we have. Now notice that h occurs in the numerator of one term and in the denominator of the other term. So this bound is not linear in h. That is quite clear. In fact, if you take h to be very small, then the round off error may get bigger and bigger. So we will have to find some Suvarna Madhya, we will have to find some value of h where this error bound does not grow too much, and yet we have a good approximation. If you remember, in one of the earlier methods, we had a similar situation and we had to find an optimal value of h. Similar optimal value of h will need to be determined in this case also. Okay, so now we are going towards other methods to solve the numerical ODEs. But whenever we have different methods, we would like to compare them with the earlier learned methods. Okay, so the device that we have for that is called the local truncation error. So let's try to understand it. So what we have is that whenever we have a numerical technique, the aim of the numerical technique is to determine approximations as accurate as possible with minimal effort. Okay, and so we have to, of course, compare various such methods and see how efficient they are. So the very first way that we will use to compare different methods is called the local truncation error. Okay, we will see why it's the local, why it's called local, why it's the truncation error. We will see all of that. What it does really is that at each step, it measures the amount by which the exact solution to the differential equation fails to satisfy the difference equation being used for the approximation at that stage. So what we have is that we have the solution which we denote by yi. We don't know the exact value, but there is some solution yi, the solution value at the point ti. We will try to put this value in the difference equation and see whether it satisfies the difference equation or not. That's what we are going to do. So we would want to know how well the approximations generated by the method will satisfy the differential equation and not the other way. Okay, so let's see what is going to happen. So not the other way, meaning that we don't want to see how far the approximate solution is from the actual solution. What we are going to see is that we are going to compute these various solutions and put them in the other equation. So if you have the exact solution, you put it in the difference equation, or if you have the approximate solution, you put it in the differential equation and see where the difference is. So this is how, of course, knowing exact solution is not possible. So we will have to use the approximate solutions and put them in the differential equation. So that's what we are going to do. And what it does is that it will serve well to determine the local error as well as the actual approximation error. So, okay, I think enough of words. Let's go and see what this, how this local truncation error is defined. So we have this initial value problem, and the difference method is given this way. You have W naught, which is alpha. Wi plus 1 is Wi plus step size into a function. So this is a general uh, approximation method. If you are looking at the Euler approximation method, the function small phi will be the function small f. For other approximation methods, you may have a different function there. Okay, so the local truncation error of this particular difference method is given to be yi plus 1 minus yi, the h phi ti yi upon h. So what we have done is that we have taken the actual solution here, put it in the difference equation, and we are computing the difference of those two and dividing by the step size. So this is going to be yi plus 1 minus yi upon h plus phi of ti yi. This is what we have. So you may feel that although we don't know what these yi are, how are we going to determine these local truncation errors? But there will typically be always an error formula which will be associated to these kind of difference equations, and so we will be using those formulae to compute these errors. So this is called a local error. This is a truncation error that is quite clear because you are taking the approximate value given of yi plus 1 by yi and taking the difference. Moreover, what it does is that it assumes that at the I step your answer is correct. So there might have been errors accumulated at every step. When we looked at the error bound, the yi plus 1 minus wi plus 1, that mod is less equal some quantity, that is the total error accumulated at every step. So for 0th step there is no error, but for the first step there is some error. For the second step, the first error will contribute something, and then there is an error of the second step, so you will get an accumulated error. What this assumes is that it assumes that at the ith stage you had the correct answer. So yi is the correct answer, and it assumes that you had the correct answer, and now you are putting this correct answer in the difference equation. So you are going to get the next approximation. It's not the correct answer for, for instance, if you are taking the Euler method, because there will be an x square by 2 y double prime at xi I. So that is a quantity which may still be non-zero. So even if you have the ith solution to be correct, y plus the I plus 1 may not be correct. But we will assume that the ith one is correct and see how far the I plus 1 goes from the actual value. That's why this is called a local error. And it's a truncation error because you are looking at the truncation at each step. Okay, so this is how this error works, that it will look at how much, it will not look at the errors which are accumulated from the previous steps, but it looks at the error only at the ith step or the I plus 1 step, depending on how you number your steps. So that's what this local truncation error does. Okay, and this is a very nice way. For instance, if you were looking at the Euler's method, then the difference equation is given by Wi plus 1 to be Wi plus h f ti wi. And now we apply the local truncation error, that would be yi plus 1 minus yi upon h f of ti yi. But remember, yi plus 1, Euler's method uses Taylor's theorem for n equal to 1. So yi plus 1 will be yi plus h f ti yi plus h square by 2 y double prime xi. So the yi gets cancelled here itself. What is left is h f ti yi. If you cancel the h in the numerator and denominator, you will have cancelled this part also, and then the other things will be there. So what we have is h by 2 y double prime at xi. And if you know that y double prime of t is bounded above by some capital M, then the local truncation error will be bounded above by h capital M by 2. This is the local truncation error for Euler's method. And so what we see is that the local truncation error in Euler's method is of the order of small h. It is really small h times a constant. So this is of the order of big O of small h. So it's of the order of h. And what we will do is that we will try to select difference equation methods for solving the initial value problems with two objectives in our mind. We would like to have local truncation errors to be order of h power p for as large p as possible. But at the same time, we don't want to have too many computations. So we will try to keep the number of calculations as well as the complexity of the calculations within a reasonable bound. This is what we are going to do. So this local truncation error will help us choosing these different difference methods. That's what we are going to have. And let me just mention one such method, which is called the higher order Taylor method, because after all, Euler's method used Taylor's method. So we will use Taylor's method for higher orders. And what we then have to assume is that this function f is n times continuously differentiable. To use Euler's method, we needed it to be only continuous. But now we assume that it is n times continuously differentiable. Taylor's theorem will give an expansion of the I+1th value of y in terms of the ith value of y, the derivative at the ith value of y, so on up to the nth derivative of the ith value of y. And the error, the truncation error, is given in terms of the n+1th derivative at some xi I. This is our standard statement of Taylor's theorem. So this is the value that we are going to put and obtain the difference equation. But you may wonder what would happen to these various derivatives of y. So these derivatives can be computed by taking various derivatives of the function f, but they will involve the function y also. So that's the only thing. You may remember my saying that y double prime, computing the bound on y double prime is a difficult thing because you don't know how the solution function y looks like. And here, in fact, we are talking about higher derivatives of y, but these computations will be computed keeping y in them. So we will see, perhaps we will not have a time to do any example in this lecture, but in the next lecture, we will see examples where the this second derivative of y, third derivative of y will be computed using various derivatives of the function f. So let me at least tell you now how these derivatives are going to be computed. Y prime t is f of t yt, y double prime t is f prime t yt, and so on up to the n+1th derivative of the function y is the nth derivative. But these are the derivatives with respect to t. Okay, so once you have this, we can put all these values of various derivatives of y as derivatives, certain derivatives of f, and this is the formula we get. And the Taylor method of order n is then the initial approximation being alpha and the I+1th approximation being h. We are going to ignore the error term. So this error term is going to be ignored, and we will have wi plus h f ti wi plus dot 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 h power n upon n factorial, the n plus n minus 1th derivative of the function f at ti wi. So this is the Taylor method, and we see that Euler's method is nothing but Taylor method of order 1. So all right, I think this is a good time to stop today's lecture, and what we will now do in the next lecture onwards is to begin with some examples, give you some idea of how Taylor methods work, and then go on to study other methods. Thank you and see you soon.